Let us look at one more example of continuous time convolution. For that, let's consider two signals shown on the screen. The first signal, that is x of t, here is a rectangular pulse bit defined from 0 to 1, that is constant as 1, whereas the second signal is defined from 0 to 2, that is taking the values as t. So let h of t be t. Now we know the formula for the convolution. The formula for the convolution of continuous time signal is y of t equals to integration x of tau h of t minus tau d tau, and this integration is from minus infinite to infinite. Now we have interpreted this equation as, first of all, we need to flip this h. Just because there's a minus here, we are treating this h as a variable of tau. Just because this t is fixed, we're calculating a value of y at fixed value of small t, and hence if we fix this small t, we treat this h as a function of tau. Because t here is a fixed value, so it will be a function of tau. So this t minus tau indicates a flipping and shifting operation. So first we need to flip h and then shift by t amount. So let's do that. So I'm drawing the flipped version of h. So it will be a mirrored version of h. So the signal would look something like this. The values here would be -2 and 0, the amplitude being 2. Now we are treating this h to be a function of tau, so this is going to be h of minus tau. So the change of variable here, so it doesn't matter what the variable is, just because it is tau, we are having this flipped version or the minus t version as something like this. Now the rest is to shift this flipped version by an amount of t. So let's do that. So let's suppose I'm having this original signal. I'm considering again the original signal. And then we need to keep this x as it is, but we need to vary this h. So I'll take this h and place it here. Now while doing this shifting, we are shifting this as per small t. So as small t, we are, let's suppose, shifting this signal all the way from leftwards towards right. So we are analyzing various cases here. So as we shift it, we are multiplying this signal. So you may see that as we shift the signal, we just note the amount of overlap, and we see that the overlap here, it goes on increasing between the two signals. It reaches maximum here and it then decreases. So let's analyze these cases one by one. So let's consider the case where there is no overlap, or the case where we are considering the t or the shift to be 0. So here let's consider various cases. I am saying that, let me extend this axis. So this will be -2. This will be anywhere. So if this is t, we are analyzing the case where this shift here, the shift here is somewhere before this 0th axis, so let it be here. So what is this axis? Here it is t, so this would be t minus 2, just because the width of this triangular pulse is 2, so this is going to be t minus 2, this point. And let's consider this case. So in this case, y of t, what would be y of t? The y of t here is nothing but we are calculating the overlap. The overlap here between the two signals, the green and the red, is 0. Therefore this integration turns out to be completely 0. So this is going to be 0 for what range of t? Well, all the range of t for which t is less than 0. So if t is less than 0, you can see that when t is less than 0, you can see that there is no overlap between these two signals. Hence the resultant y of t is going to be 0. So let this be case 1. So in case 1, we are considering the case where t was less than 0. So this is case 1. Let's analyze another cases. Now this is not the only case that we are going to have. Let's consider another case. So let's take the same signal, and now instead of having the overlap of t being less than 0, we will have different overlap. So let's suppose now I'm erasing this and I'm considering the signal, this h, to be shifted some more. So I'm considering this whole signal and shifting some more. So let's consider this case where this t here, small t, is somewhere between 0 to 1, where the overlap would be this portion. So the point here is considering I'm t, and what would be this point? This will be of course t minus 2, but the overlap that you can see here is between 0 to t. So the integration limits will be from 0 to t, and we are analyzing the case where this small t is between 0 to 1. So let's take this as case 2. This is the case where the t is ranging from t is greater than 0, greater than equals to 2, but less than equals to 1. So we're considering that case where this point here, the shift point, is between 0 to 1. Now what would be the integration there? So the integration would be y of t equals to integration will be in the range of overlap, that is 0 to t, just because this overlap here can be anywhere between 0 to 1. So that is, let it be t. Now we know the formula for convolution, x of tau into h of t minus tau, and we know that x of tau here, and you should not forget that this axis here is with respect to tau now. So this x of tau is 1 in this range, and whereas h of t, we know that that is t, but instead of t we need to consider t minus tau. So the signal is going to be here x of tau, that is 1, multiplied by h of t minus tau. So we know that h of t is t, so we need to consider t minus tau, and this is going to be x of tau into t h of t minus tau. So this portion here is x of tau, whereas this portion here is h of t minus tau. Now we can easily solve this integration, and that turns out to be integration from 0 to t minus tau d tau. That turns out to be t square minus t square by 2. So y of t equals to t square by 2 for the range between 0 to 1. So you have calculated y of t for the range 0 to 1. Similarly, we can analyze the other cases. So let's analyze another case where t is going to be different. So we are analyzing the case where the signal here, the shift between the signal is now different. So let's take the case where now the shift between these two signals, or the overlap, is complete. So it is greater than 1. Now we are considering the case where the overlap is greater than 1. So let's take the case here. Now we have considered the case 1 as where there was no overlap. So overlap was nil. Now the second case that we have considered was the one where there was some overlap and the t point or the shift point was there somewhere between 0 to 1. Now let's consider the case where the overlap is such that this shift point here, that is the end point of triangle, is somewhere greater than 1 and less than 2. So let's consider the case somewhere here. Now this overlap will be having the range from, you can see here, we're considering this overlap. Let's label that. So if this is going to, this overlap is going to be from, let this be t. If this is t, this is going to be t minus 2, and this will continue. This overlap will continue till the point where t reaches the value of 2. So we are now analyzing the case 3 where t is greater than 1 but less than 2. So we are analyzing this case here. You can, once again, let me demonstrate it once again. So this signal here, I am shifting. We have considered the case 1 as the case where there is no overlap. We have considered the case 2 as where there is an overlap in such a way that the t here lies between 0 to 1, and now we are considering the case where this t lies greater than 1 but less than 2. So the limits of integration similarly would be y of t equals to, the limit of integration is the amount of overlap. So what is the amount of overlap here? You can see that there is complete overlap between 0 to 1. So the limits will be from 0 to 1, and this signal is going to be x of tau into h of t minus tau, that is going to be 1 into t minus tau d tau. So this expression is going to be t. You can see that is going to be t minus half. So this is valid only for t between 1 to 2. Very simple here, because the overlap here exists between 0 to 1, so the integration limits are between 0 to 1. Therefore, by solving this integration, we can see that the values are going to be t minus half. So this is valid only for the range of t being from 1 to 2. So this is valid only for the range between 1 to 2. Let's analyze the other case. So we are considering another case. So for that, let me consider the same signal. Now the overlap range that we are considering here is different. Now in case 1, we have considered the overlap to be somewhere here. There was no overlap. For case 2, we have considered the overlap being such that the point T here, you should note that the point T is this point is T. Now we are considering the case where the overlap is such that the point T is after 2. So we have initially considered the case 1 as the one in which there was no overlap. That is the case where T was less than 0. In case 1, we have considered the case where the overlap is such that the small t is between 0 to 1. After that, we have considered the case where the small t was in the range such that it was greater than 1 but less than 2. Now we are considering the case where the small t is greater than 2 but less than 3, because this will be the overlap, greater than 2 but less than 3. So I'll place it somewhere here. You can see that the overlap here is this much. Now what is this point? Let that be t. If that is t, this is going to be t minus 2. So now we are considering the case, let it be case 4, where t is lying from 2 to 3. Now if that is the case, the integration is going to be y of t equals to, now check the overlap. You check the overlap here. The overlap is between t minus 2 to 1. So that will be the maximum overlap that can happen. So it will be from t minus 2 to 1. Rest of the things remains the same. That is t minus tau d tau. That is going to be equals to, now we can solve this. We can solve this as t into 1 minus t minus 2, that is t plus 2 here, and that is going to be minus tau square by 2. So that is going to be 1 minus t minus 2 square and by 2. So this is going to be equals to t minus t square. So it is going to be equals to 2 plus 1, that is 3t, minus t square minus half, the plus t square by 2 minus 2t by 2, that is t, plus 4 by 2, that is 2. So this, if we segregate the terms of t, that is going to be 2t and if we segregate the terms of t square, that is going to be plus so it is going to be minus t square by 2, and the rest, that is half plus minus half plus 2, is going to be plus 3 by 2. Now this will be the case if and only if this small t is in the range of 2 to 3. So this is the equation of y of t if y of t lies between 2 to 3. Now let's consider the final case here where there is an overlap which exceeds these limits. So I'm considering now the case. For that, I'll take the same signal again, and I'll see that this signal is now completely getting overlapped over the limits. So for the case where t is higher than 3, there is no overlap. So in this case, the signal is going to be 0. So I'm analyzing this case. Let me extend this axis. So I'm analyzing now the case where this small t is going to be higher. So case 5, I'm analyzing the case where t is greater than or equals to 3. So here, if this t, this is going to be t minus 2, and I'm analyzing the case where this t is higher than 3. So in that case, we see that there is no overlap, so y of t is going to be 0. So y of t is going to be 0 for t higher than equals to 3. Now we have got all the cases of overlaps. There is no other case that is remaining. So the resultant signal y of t would be the summation of all these three. Not a summation, but we'll have to keep in consideration all the ranges of y of t. So the resultant y of t would be, that y of t is going to be 0 for t less than or equals to 0. It is going to be t square by 2 for t being in range of 1 to 2. We have also seen the case 3 here where the signal is t minus half. So it is going to be t minus half when t is going to be between 2 to 3. And the case 4 here, we have seen that it is going to be 2t minus t square by 2 plus 3 by 2. So it is going to be 2t minus t square by 2 plus 3 by 2 in the range of t being the ranges here are not written properly. So here it is going to be from 0 to 1. Here it is going to be from 1 to 2, and from 2 to 3 it is going to be 2t minus t square by 2 plus 3 by 2, and it is going to be again 0 for t greater than or equals to 0. Now this is the complete solution. Now let me once again summarize what we have done so far. See, we were having this signal, so let me copy paste it here. Now we were having this signal. Now we have analyzed different cases here. So we have taken the signal in red, and we have tried to shift this signal and calculate the amount of overlap. So the first case here is the one where there is no overlap. That's the point where this t, the small t here, is this point, because after flipping, the shifting starts from here, the axis point. So I'm considering the first case where there is no overlap between this red and the green signal. So this case, from left if we are shifting, there is no overlap, and the overlap actually starts from 0th point. So before t equals to less than or equal to 0, the signal will be 0, and if the overlap exceeds from 0, the overlap is going to be from 0 and somewhere in the middle, this area. So that is this case. After that, we have considered the case where the overlap is exceeding and getting completely covered the signal x of t. That means the overlap is such that the small t is in the range from 1 to 2. So we have considered this case. So here if we consider this signal, this is t, and this t is between 1 to 2, you can say, and we can see that the overlap here is this portion. Now if you calculate that integration, it will turn out to be this part. Similarly, we have taken the other case as the case where the overlap is now exceeded 2, so it is somewhere here. So that is the point where small t is greater than 2 but less than 3, so the overlap will be this much portion. And the last case that we have considered is where the overlap exceeds. So it is like this. So this signal, I have considered these two signals to be somewhere here. So there is no overlap between these two. So this is the case. The last case is this one. So that's the summary of the operation that we have performed. So we shall see more into these convolution properties in the next module. See you in the next module then. Thank you.